Okay, so this paper is called Modeling and Extending the RCA Mark II Sound Effects Filter. And this is a paper by me, Werner, and some collaborators, Ezra, Teboul, Seth, Cluett, and Azelborn. And so the Columbia Music Center in New York has this huge archival holding of documents, recordings, and electronic equipment from their history, and also from the predecessor to that center, which is the Columbia Princeton Electronic Music Center. Obviously, that was a joint venture between them and Princeton University. And they're looking to do some archival work. Actually, they've started doing some archival work, trying to understand this, what's in there, and build some new things out of the old gear, and just kind of like understand their own history better. And this part of the work is part of a larger modeling project that aims to understand some of the gear and expand access to it, because a lot of this was stuff that was either completely unique, maybe one in the world, or very rare, and most people never had access to it. So this paper has a little bit of everything. We've got to search in the archive. We've got to analyze some circuits. We have to understand how some circuits were designed. There's a little bit of hardware hacking, and some modeling, and even a little bit of image processing, and finally a giant 3-ton synthesizer bolted to the floor of an office for the last 65 years. So this is that synthesizer, the RCA Mark II sound synthesizer, sometimes called Victor. The founders of the CPEMC, Vladimir Yuzikevsky and Otto Luning, installed it in 1957, and it was built by some engineers at the RCA Corporation, Harry Olson, Herbert Bellar, and Jim Timmons. And this was a big deal because there weren't a lot of synthesizers back then, and it was extremely expensive, and there was only one ever made. And so this, on an institutional level, the acquisition of this gear was an important event that helped establish CPEMC as one of the world's foremost experimental composition spaces. And it was one of the first experimental electronic music studios in the United States, which kind of got into that a little bit later than Europe. And here's some pictures of this thing today, bolted to the floor of the office in CMC still, just for fun. So the purpose of this paper in particular is to model part of this synthesizer called the sound effects filter. In fact, the whole giant synthesizer has 4 nearly identical sound effects filters. And what they are is bandpass filters, and their controls, if you read the schematics from the Columbia archives, are 2 11-throw discrete switches, one that controls a high-pass cutoff, one that controls a low-pass cutoff. But then if you get in there, there's actually a couple switches on the front, and so the first thing we ask ourselves is, what are these switches? Do they turn the unit on? No. What are they doing? So more on that in a minute. So what the circuit is a passive resistively terminated inductor capacitor circuit made of 2 of these so-called T stages, so-called because they're shaped like T's. There's one T, there's the next T, and then it's resistively terminated, so it's got a source resistance and a termination resistance. And then these 11-pole switches 11-throw switches sort of allow you just to switch in different sets of capacitors and inductors. There's a schematic up here. It's basically showing, it selects a different capacitor depending on where the switch is at. And they're 3-pole switches as well, in that each one is controlling 2 capacitors and 1 inductor, or 2 inductors and 1 capacitor. So this is what the schematic says. When you get in there, there's some mysterious components, and it turns out after some board tracing, this is what's really going on in the circuit. There's actually 4 stages. A schematic lied to us, not the first time. So there's actually 2 more T stages that are kind of fixed at a particular, they don't have different values controlled by a knob. They're just on or off. So you switch the 2 switches, either switch them out, in which case there's just a short bridging across them, or it switches them in which case you get another T in cascade. So you can actually have up to 4 in cascade. And it doesn't say it in the schematics, but a little bit of sleuthing and digging through some dusty old books, and you can find out this is actually something called a constant K circuit design. This was quite a popular type of passive LC ladder circuit design, which starts with something called the K parameter, and that's constant. Each of the stages in this circuit has the same K, and the K is also equal to the source and the termination impedance. So here, 560 ohms. And this is a chart from the paper. I guess the notation is a little bit different. Z and Y are the series impedance and shunt admittance. So Z is the same as Z1, and Y is the same as 1 over Z2. Little mistake there. So it's a T shape, and then the cutoff frequencies of these depend on the component values. But all of them have this like K parameter in constant, that in common between them. Or that's the way it's supposed to work. You can build it without that, and something happens. But the by the book design procedures to fix that at a constant, and in that way terminate them correctly on one another. So it was a big win to find the schematics because it's a little bit. These things are fragile and rare, and we can't exactly go busting them open. And the information in the journal articles that Ballar and Olson published are pretty scant on information. So it was great. We managed to find, I think, the one copy in the world. Maybe there's something else in the RCA archives, but we found the actual schematic of this thing. But still not enough to model it. There's a couple problems. One problem is that some of the component values aren't labeled. So the capacitor values are given, but the inductor values are not given. The RCA engineers weren't exactly going out to Radio Shack and buying pre-made inductors back in the day. When you wanted an inductor of a certain value, you bought a toroidal core, or a different type of inductor core, and you wound a certain number of windings around it. So there's instructions for how to build the inductors, but there's no indication of what the inductor's values are. So there's this little bit of a triangulation process that went on here. We're able to look up some of these constants that relate the square of the turn ratio to this parameter AL for inductive cores. And we're also able to use a leap of intuition to realize that this thing looks like a constant K filter, and it has a constant input and output termination. So I wonder if the K parameter is going to be the same as those for the rest of the stages. And it turns out if you make those guesses and tabulate some of these things, you end up, this is a lot of numbers, sorry, but for every stage and every setting, here's the calculated K at the end of this. And so it turns out they are all very close to 560 ohms, so this kind of confirms that it's a constant K design. There's a lot of information in this table. Basically, the schematics include information about the ideal way the circuit should be designed. That's this actual column, and then a way it's actually, desired is the way it's supposed to be designed. Then it has an actual way it's built because capacitors are manufactured in discrete values. So if you want a 1.62 microfarad capacitor, best we can do is to put a 1, 0.5, and 0.1 in series and get pretty close, and so on. So after a little bit of sleuthing and digging in the archives, we now know the circuit topology, and we now know all the component values. So what's next? It's time to model this thing. So we've already had a good tutorial on a lot of the principles of wave digital filters, so I won't go into too much of that here, but maybe I'll talk a little bit about how you get to a structure from a circuit, because that wasn't emphasized in the tutorial the other day. So you take your circuit and you make a graph out of it. So every circuit node becomes a node in the graph, and every circuit element becomes an edge in the graph. Then you perform this thing called SPQR procedure, where you create a different type of rooted tree structure graph from this. That's the second layer here. And so now we have elements as leaves in the tree, and then series and parallel connections as nodes. Then you can split this apart, creating this so-called search for split components, and that's now isomorphic to this wave digital filter structure, which is also, you can almost even just scrunch the circuit components around and redraw the wires. Or maybe Georg can tell me if I'm saying this wrong, but this is a different embedding of the circuit onto the sheet of paper than the normal way you would have drawn this schematic. And you can see that that bottom two rows, they basically look the same. So if you just draw the wires in a different place, it reveals the wave digital filter structure. And so at this point, you can either go and write a lot of code, or there's apparently some libraries out there to build the wave digital filter for you. So we used a library called WD Models, implemented by Dirk Rosenberg. And Dirk has a SMC paper on this. And this is a cool little library that basically allows you to specify a wave digital filter tree as a tree. So this is the key line from the code. It basically says the tree is a voltage source in series with capacitor HPM1 and the parallel combination of inductor HPM and the series combination of HPM2 with the series combination So it's basically going and like almost in plain English writing through what this bottom block diagram is saying. So this was nice. Basically, we were done in 5 minutes once we had done all the sleuthing. And so yeah, we wanted to test that this thing worked right. So we had a couple different magnitude responses we could look at. Interestingly, the schematics included some magnitude responses. It's unclear whether they're measured magnitude responses from 1957 or whether they're ideal. It's not totally clear. They're like drawn in this funny way where the lines kind of just start and stop in weird places. Is that because an oscilloscope or a meter hit the noise floor at that point and they stopped drawing it? Is it because it was a freehand drawing? We don't know. So we have that, and that's one piece of information. And we used image processing software that like aligns so this is our picture, and it's a little bit messed up, and it's a little bit askew, and it's a little bit like not flat on the scanning bed. So we use this image processing software to flatten it and to extract the data curves from this. We also were able to get in there and measure the real device, and we just put like a 1 minute long white noise sequence into it and used like Welch's method to extract the power spectral density. And then we also just measured kind of impulse response of the model. So we've got all these different families of curves now. We can take a look. And so this is too much information probably, but you've got all the different settings of the switches. You've got all the different settings we're kind of sweeping the high pass knob, sweeping the low pass knob, and then either with the other one in an extremal position or in the middle. Let's maybe just look at one of these closely. So the dotted one is the model. The solid one's the measured 2022 measurement, and the dash dash is the what's written in the schematic. And they match pretty well, but not perfect. It's a little bit of a mystery still. Do they not match because the model is not complete? Maybe the inductors have some series resistance or some like Q factor. Maybe there's parasitics in the circuit. Or do they not match because the original schematic drawing was a freehand drawing and it wasn't supposed to be a scientific measurement? It has some telltale things like the slopes of the lines when they're in the cutoff region aren't like at 6 decibels per octave, or I think that should be 12 here. They're at like 13 and a half. So like maybe that's evidence that was a freehand drawing and not a measurement. But in any case, it's parameterized in mostly the right way. And it captures like the bulk of that behavior, whether or not that behavior is right. So a couple, this is our little foray into circuit bending here. We've got a couple extensions we made. So there's actually some precedent from the founder of the Columbia Princeton Electronic Music Center, Yusachevsky, who wrote in the 50s that they deliberately mismatched the impedances of the devices to get more colorful, interesting distortions out of these filters. So we took some inspiration from that and just the general, isn't it fun to circuit bend these things? And we said, okay, well, we've got this model, let's just change those impedances up. And so you can see that like adds some cool resonances. We get the response of the original filter. It's not actually super exciting. It's like a fifth order filter kind of thing. It's a little steeper than a normal filter, but it's not like completely exciting. But it gets weird and has this kind of vocal double formant quality when you start mismatching the impedances. And now that a couple other extensions I'll just mention as I wrap up. Now that we know this thing was built by Constant K Design, we can abstract it and say, okay, let's have twice as many low pass stages, let's have 5 times as many high pass stages, and you can make a sort of like fantasy version of the thing. Like, what if they were willing to make a 410 synthesizer and they had a bunch more inductors lying around. How could you have extended this version to have like steeper cutoffs or less steep cutoffs? And I'm pretty much out of time, but I will maybe just play like 1 minute of this demo. Oh. So it gets pretty colorful when you start mismatching those impedances. And where's the slides?
Was that a recording of a speaker?
It may have been, yeah. Okay, so to wrap it up, we've modeled this thing. The behavior mostly matches the original. It's possible there could be some ways to refine it, perhaps with the inductors. And in the future, we'll continue to work on modeling other pieces of the RCA Mark II. It's got all sorts of other interesting filters and some cool resonators and sound processing devices, and those are next on the agenda. And one takeaway, top tip for people doing virtual analog from this paper, which didn't have a lot of technical content, a top tip is that you can't always trust schematics. Sometimes schematics are liars.
Thank you for the presentation. I'm actually interested in the little demo that you did. What was the input?
Yeah, the input was just white noise. There's one in the back.
So hi, Kurt. Could you elaborate a bit more on the dynamic behavior of your model? So do you notice any idiosyncrasy while tweaking with your parameters, or if it could be noticed, I mean, because of course one should compare with the original circuit, but if you could detail a bit more about this.
Could you repeat that? I couldn't quite hear you.
I think that you were changing parameters during. So did you? Could you just elaborate a bit more on or your impressions in front of the dynamic behavior of the circuit of your model? I mean.
Yeah. So we were in the demo there. We were just kind of changing the knobs somewhat randomly around, and then varying some of the resistances when it kind of gets more resonant and then less resonant. That's sweeping the resistance values. I can't really comment on like the accuracy of the model during the moment of the change. I think something I can tell you though is like because of the way these variable inductances and capacitances are implemented, they're not actually they're not actually variable. For the capacitors, as you turn the knob, you just switch in another bank of capacitors. So you're kind of switching in a fresh, uncharged capacitor, if you will. Meanwhile, for the inductors, as you change the inductance, kind of in 11 settings, there's like 3 inductors, and it's tapped off at various places on the winding. So if you switch inductances, you may be switching to like a partially magnetized inductor, if you will. So we didn't get deep enough to like examine that, but it could be that like the more accurate behavior kind of has clicks and pops because you're just putting in something that's not charged up, but you may want to like, for like quality of life as a user, you might also want the option to like smooth it out by using power waves in the simulation or something that kind of like attempts to like keep things constant and avoid those clicks. But it's an aesthetic question. The clicks may be accurate and they may also sound kind of cool. Okay, one last one from Dan, and then I think we're over time.
Just a clarification, when you said that they utilized the impedance mismatch to, because they like the distortions, did you mean distortions in the frequency response or actually like time domain nonlinearity style distortion?
Well, this is the entire quote here. So Kevsky is not around to ask what it meant, but we assumed that this meant distortions in the sense of the flat passband getting messed up, because back in the 50s, all these things were impedance matched devices, not impedance bridged devices. So the statement kind of makes sense. If you mess with the impedances, you get that version of maybe what you wouldn't in English normally call a distortion, but which is sometimes called a distortion, is like the messing up of a frequency response.
I feel like they used to call that distortion, and we don't anymore. But
Yeah, I think it's a word whose meaning has changed over time.
Thank you.
Okay, that's the end of our first session. Thank you, everybody.